In this section, we're going to talk about functions of several variables. Now, previously we had talked about functions where we plug in one variable, vector valued functions, right? So previously we talked about functions that look like maybe, for example, r of t equals 2t comma 3t squared plus 1. This is a vector valued function. Notice it takes in as input a single value and outputs two values. It outputs a vector, right? Starting in this chapter, we're going to think about these functions of several variables. So now we'll look at functions where we plug in, say, two values and output one. So maybe x squared plus 3xy plus y cubed, for example. This is a function, in this case, of two variables. Notice it takes in two variables and the output is a single value. Okay, it outputs a single value. All right? Let's define this. A function of two variables z equals f of xy has two variables as input and one variable as output. Okay, notice just like with single variable functions, if I were to write f of x equals 3x squared plus 2, you know x is what we plug in, but then what it spits out, the f of x value, we treat as the y value, right? Similarly, in this case, we are plugging in two values, x and y. The output value, the f of xy value, is what we treat as the z value. Okay? The domain of the function is the set of all xy pairs. That we are allowed to plug into the function. Sometimes we explicitly set the domain. We'll say, you know, a function, this is the function, and these specifically are the values we are allowed to plug into the function. But most of the time in this class and in other classes, we use an implicit domain, which is the domain is all the values that you can plug into the function without it breaking, without something happening like division by 0 or a negative under a square root, something like that. Okay? So most of the time we use that implicit domain. The domain is everything that you could plug in without the function breaking in some way. Okay? And of course the range is the set of all output values. Okay? So let's just play with it just a little bit. Let's do a quick example. Just take a look at one two variable function. We'll have f of xy equal, let's do 3x squared plus 2xy minus 1 over x. Okay? And let's consider what f of 2 comma negative 3 is. Okay? So f of 2 comma negative 3, all I do is I'm going to plug in 2 for the x. I'm going to plug in negative 3 for the y. Just like with a single variable function. I just have two values I'm plugging in instead of just one. Okay? So I'm going to plug in 2 for the x. So every time I see a x, I plug in 2. And I plug in negative 3 for the y. Every time I see a y, I plug in negative 3. All right? If we just evaluate this real quick, 3 times 2 squared, that's 12. Negative 3 times 2 times 2, that's a negative 12. And then I have the minus 1/2. 12 and negative 12 cancel. And so the output value is negative 1/2. All right? What this is telling us is that a point that satisfies the function is xyz equals, I plugged in 2 negative 3 for the x and y, and the output value, the function value, the z value, is negative 1/2. Okay? We can think about this function as a surface. The surface is all the x, y, z ordered triples that pair together, that satisfy the function. If I plug in an x and y, the z value that goes with it, if I put all that x, y, z together, that point is on the surface. The set of all such points is the surface of the function. Let's take a look at what this particular surface would look like. Okay, so we have f of xy equals 3x squared plus 2xy minus 1 over x. Okay, we get a really kind of funky looking surface here. Let me make it a little bigger. All right, it actually comes in two pieces, it looks like. Maybe if I zoom out, they'll link together. No, that really does look like two pieces. Okay, really interesting looking surface. You could see there are places where the 3D graphing calculator actually struggles to plot it because it has some really interesting geometry. Okay, but I wanted to just emphasize that we do actually get a surface here. Okay, and the particular point we found, 2 negative 3 negative 1/2, is a point that lies on the surface. 2 negative 3 negative 1/2. And you could see if I move over here, that point right there, it's actually on the surface. Okay, let me make it a little bigger to make it a little easier to see. There we go. The point actually on the surface. So the surface represents the set of all points for which the if we plug in an x and y, that is the z that pops out, the z that satisfies the function. Okay. And before we move on, I just want to say one more thing in terms of notation. Most of the time, we will see this expressed a function as f of xy. We will separately describe the two variables we're plugging in. But sometimes, because we're plugging in xy, that is a set of two variables. We can represent a set of two variables as a vector. So sometimes we want to use our vector arithmetic. Sometimes a function is easier to express in terms of vector arithmetic. And so we might write something like, instead of f of xy, we might write f of, say, r, where it's understood that vector r is the vector with variables x and y. But this would allow us to describe the function in terms of that vector instead of having to break it down in terms of x and y. Sometimes this is simpler. Sometimes the particular function we're describing is better described using vector notation. next, let's take a look at a couple of examples where we need to graph the domains of some of these two variable functions, all right? So first off, note that we do want to graph the domain. In single variable functions, we usually want to describe the domain using interval notation, but multivariate functions, the domains are a little more complicated. So we usually want to graph them. That's usually the best way to communicate the information, okay? Second, notice that this isn't an f of xy, this is a z, all right? Just like sometimes we will have y as a function of x and we write y instead of f of x, right? I could write y equals 2x squared plus 3x, or I could write f of x equals 2x squared plus 3x. Same thing here. Instead of f of xy, I have z. But z is a function of x and y because I'm able to get z by itself on one side of this equation. And for any xy I plug in, only one z value corresponds to it. I only get one z value for a particular x and y value. That means z is a function of x and y. Okay? All right, so let's graph the domain. So as I had previously said, the usual way we think about the domain for a function like this is we use the implicit domain. It's all the values of x and y we are allowed to plug in. So we have to look for things like a 0 in the denominator. We're not allowed zeros in the denominator. We are not allowed to have negatives under any even roots. So square roots, fourth roots, sixth roots, anything like that, okay? And then we need to watch out for special functions. So special functions like tangent or the natural log function. These have domain requirements of their own. So we got to pay attention to those. All right. Now, in this case, the only thing I have to worry about is a denominator. I need to make sure that denominator is not 0. Notice I don't care what the numerator is doing. Numerator, because it has nothing else going on up there, there's no square roots, there's no special functions, I really don't care what's up there. For its domain, I only care about where the function is going to break. And the only place that this function can break is if I choose an x and y that would make the denominator 0. So what I'm going to do is I'm going to find when the function breaks and then make sure that is not in my domain. So this function breaks when the denominator equals 0. So when x minus y equals 0. Okay? So if I move the y over, I have the line y equals x. So whenever x and y are the same value, that's where my function breaks. Okay, so if I were to plot this in the xy plane to illustrate all the values that I can plug in, I want to make sure that whenever x equals y, that is not in my domain. All right, so graphically, x equals y is a line, right? It's this line right here. Okay, so notice it's dotted. I do not want to pick the xy values there, but I do want to pick them everywhere else. So I'm going to shade where I do want to pick xy values. Okay, so all on this side, all on this side, that's okay. All of these x and y's are okay. I just need to stay away from the line y equals x. Okay, because on that line, the denominator of this function will be 0. Okay, so those are the x and y's I'm allowed to plug in. Let's do one more. Here I want to graph the domain of the function h of xy equals natural log of 16 minus 4x squared minus y squared. All right, so again, we need to look for where the function breaks. In this case, I don't have any zeros in the denominator. That could happen, right? I don't have a denominator, so a 0 in the denominator is not a possibility. How about negatives under a square root? Okay, or any even root. Again, no roots, so I don't have to worry about it. I do, though, have a special function. Natural log is a special function. And I need to make sure that I only plug into that special function what is allowed to be plugged in. Okay? So remember what the graph of natural log of x looks like. There is an asymptote on the y-axis. And then the graph looks something like this. We just need a rough idea of what the graph looks like. It doesn't have to be perfect. Okay, so this is the function y equals natural log of x. What this does, what this tells us, is it tells us what we are allowed to plug in to the natural log of x. What x's are we plugging into this function? Notice we can't plug in any negative values. We're only plugging in positive values. Also, not 0, right? 0 is an asymptote. Where x equals 0, that's an asymptote. Okay? So based on this picture, the domain of the natural log is everything bigger than 0. All right? Now, how does that relate to what we're doing over here? We have a natural log function, so what are we allowed to plug in? The only things we are allowed to plug in are numbers bigger than 0. Okay? So in this case, we need to make sure that what we're plugging in this case, 16 minus 4x squared minus y squared is greater than or equal to 0. As long as that happens, then everything will be okay. All right? The natural log function will evaluate fine, and we will get an answer for our multivariate function here. Okay? But we need to make sure, because the domain of the natural log is non-negative, actually, not just non-negative, positive, 0 is not included. Okay? We need to make sure this holds true. And actually, I just realized I made a mistake. I said greater than or equal to 0. That's wrong. It has to be strictly greater than 0. I am not allowed to plug in 0 in a natural logarithm. That's why I have a parenthesis here. Okay? That asymptote, I can approach it, but I can never reach it. So I need to make sure this is strictly greater than 0. Okay? All right, so how do we go about graphing something like this? So what we want to do is we want to, for the moment, kind of ignore that inequality. Okay, kind of pretend that it's an equality. So I'm going to move the 4x squared and the y squared over to the other side. Now, if this were an equality, I would have an ellipse, right? And if I wanted to put it in standard form, I could divide by 16. So if I divide by both sides by 16, I get 1 is greater than x squared over 4 plus y squared over 16. By thinking about this as an equal sign, that tells me the boundary of the region that I want to use. Okay? So let's graph that boundary. So this is an ellipse centered at the origin. And so I'm going to go 2 units in the x direction. In both directions. And then square root of 16 is 4, so I go 4 units in the y direction. Okay, and the ellipse that goes through all of these is the boundary of the region that I'm okay with plugging in. All right? But we got to be careful here. We have to think, are we okay with plugging in values on the boundary or not? How did we get this boundary? This boundary is what happens when I set 1 equal to x squared over 4 plus y squared over 16. Am I okay with 1 being equal to x squared over 4 plus y squared over 16? No, I want 1 to be greater than x squared over 4 plus y squared over 16. So because I don't have that equality, I don't have an or equal to, I'm not going to do a solid line as I've drawn here. I'm going to draw a dotted line. That indicates, hey, this is the boundary, but I actually don't want to include the boundary. The boundary is not okay. The dotted line says, this is not what I want. Okay? Any point on the boundary does not satisfy this inequality, which means we would not be allowed to plug it into natural log function, which means it would not be in the domain of our original function. All right? Okay. That tells us our boundary, but which side do we shade? Notice we've split our xy plane into two regions. We have the region outside the ellipse and the region inside the ellipse. Now, one of those regions we're okay to plug into our function. The other one we're not. How do we know which is which? The easiest way to do this is to plug in a test point. Pick one point in one of your regions. Doesn't matter which point, doesn't matter which region. Just make sure it's not on the boundary. We already know what's going on the boundary. Boundary is not okay, that's why it's dotted. Okay, so we either want the inside of the ellipse or the outside of the ellipse. In this case, the easiest point that I see to plug in is 0, 0. So I'm going to plug in 0, 0. That's going to be my test point. So I'm going to plug in here. I get 1 greater than 0 squared over 4 plus 0 squared over 16. That's 1 is greater than 0. That is a true statement. Okay? So 0, 0 makes this inequality true, which means it would be a point that I would be allowed to plug into the natural log function. It would be a point in the domain. Right? Because that 1 point works, every point in this interior region must work. So I'm going to shade the interior here. Okay. Now, if 0, 0 didn't work, then that must mean no point in the interior region must work. And instead, it must be the exterior region that works. And so I would shade the exterior region. All right. So you just need one test point to decide whether it's the interior or the exterior region that is in the domain. All right, plug in that one test point. If it satisfies the inequality, then that 1 point is in the domain, so the whole region of that point is in the domain, right? If you plug in the point and the inequality is not true, the inequality is not satisfied, then that 1 point is not in the domain, and the whole region will have the same behavior. The whole region would not be in the domain also. All right? So this, in this case, this is a picture of our domain. The domain of this function is just the interior of this ellipse. Those are the only xy points that I could plug into this function without the function breaking. To help us understand the graphs of the surfaces of these two variable functions, we can use a tool that we've actually already learned about when we learned about quadric surfaces. We can use traces. Okay. Just as a quick review, the idea here is if we have some function z equals f of xy, rather than dealing with all three variables at once, we could limit ourselves to just two variables at a time by looking at the cross section through one of the planes parallel to the coordinate planes. So for example, I could look at the trace through the plane x equals 2 by just setting all my x's equal to 2. Right? Now that gives me a relationship, an equation of just two variables. And I'm great at graphing equations of two variables. We've had a lot of practice with that. And that gives us an idea of the cross section at x equals 2. And with enough cross sections, with enough of these traces, you get an idea of how to reconstruct the full the full surface, right? So x equals 2, or I could do z equals 5. I just set the z equal to 5, and again, I have a equation of only two variables, in this case, x and y. And I could do that for y also. And get an equation of just x and z. Okay? In the special case of these two variable functions, we actually give traces special names. We call traces of let me rephrase that. We call traces where we set z equal to a constant. Level curves of the function. Okay, so the special traces where we set the function value, the z value, equal to a constant, we call those particular kinds of traces level curves. Okay, and to distinguish level curves between other traces where we set x or y equal to a constant, we call those other traces, we're going to call them vertical traces. We call traces where we set x or y equal to a constant vertical traces in particular. Okay. Why vertical traces? Because if you're looking at the intersection of your surface and one of these planes where x is equal to a constant or y is equal to a constant, so say maybe this y value right here, okay, then the plane would be vertical. Whereas if we're setting z equal to a constant, the plane where z equals to a constant is horizontal. Okay? And so that's why we call setting x equal to a constant or y equal to a constant vertical traces. All right? Now, these level curves in particular, they actually end up being pretty useful. And if we could put lots of these level curves together, we get a height map or a contour plot of the surface. So we actually have some, you probably have intuition with these height maps or contour plots. We see them sometimes in actual 2D maps to indicate the heights at different places in an actual map of a landscape. Okay, so here's an example of a contour plot or a height map for an actual geological landscape. Right? Now you have some intuition on this. The different lines here indicate a set height. If you look carefully enough, it's a little hard to see because it's not a super high quality picture. But if you look carefully enough, these lines have different values associated with them. Those are the heights at that level. Okay? So maybe at this, everywhere on this line here, in this curve, that represents where the landscape is maybe 200 meters above sea level. Okay? Notice you can tell a lot about what's going on here by the height map, by the contour map. Over here, in this region, the lines are really close together. That means it's gaining height really quickly, right? It's changing in height really quickly. Whereas over here, where they're more spread out, the height is changing more slowly. Okay? But by constructing these contour plots, you can almost see the landscape. And if we did this for a surface by plotting lots of level curves, we can see the change of the surface. Let's take a look at an example with a contour map. So here we have a function f, and graphed here is the contour map for the function f. So we want to use the contour map to estimate the value of f(3,1). But first, let's make clear what's going on here. Okay, notice that each contour is labeled. That is the level curve that contour is representing. Okay, so for example, 24 here, that's where f of xy equals 24. That curve represents all the points on the surface with a z value of 24. All right. So in this particular example, we want to estimate f of 3, 1. So here's our x-axis, here's our y-axis, here's x equals 3, here's x equals 1. We want to estimate this point right here. Okay, what is the z value at that point, the function value at that point? Okay, well, it is in between two curves, this curve here and this curve here. Okay, so this curve here, if we follow it around, we can see it has a function value of 24. So this curve all the way around, its function value is 24. And then this curve all the way around, if we trace it all the way around, its function value is 32. So every xy point on that circle, if we plug it into the function, the corresponding function value or z value is 32. Okay, and we could see that just looking at it, we're increasing going out from, looks like this is the center. Okay, we go 8, and then eventually we reach 16, 24, 32, and eventually we reach 40, right? So we're increasing as we go further along, and that matches what we have here. So this function value should be somewhere between 24 and 32. Now, it looks to me like it's a little closer to 32. So if I were to estimate this, I'd maybe say 29. Okay, it is an estimate. It doesn't have to be exact. Okay, so maybe f of 3,1 is approximately 29. Okay, that's a good estimate. But let's do something the problem doesn't ask for. Let's use our contour plot to reconstruct the surface. Okay, right now this is just a two-dimensional plot that communicates the height at certain levels. But it isn't a full three-dimensional image, right? So let's kind of draw the three-dimensional surface that this might represent. Okay. So what do we notice? With each level, we have, each level is represented by circles, right? But the circles don't share the same center. So over on this side, notice the levels are real close together. That means I'm increasing my height, my z value, my function value very quickly, from 8 to 16 to 24 to 32 to 40, very, very quickly. Okay, but in this direction, I'm much slower. I do increase, but it takes me a lot longer to get there. I have to travel a lot farther. Okay, now I am increasing. It looks like the center of the lowest circle is around y equals 1. So here's my x-axis, here's my y-axis, here's my z-axis. Y equals 1 is right here. Let's say this is y equals 8. Okay, so my first circle would be right about here. Okay, and then my next circle is at level 16. And it's a little further left, but a lot further right. Goes out 2, 3, 4, about there. Okay, and then the next level, next height is 24. So I'm going up by 8 at each level here. Okay, and 24, it's a little less, a little further in the negative direction of the y-axis, but it's a lot further in the positive direction of the y-axis. Okay, so a little further in the negative direction, but a lot further in the y direction, something like that. And maybe I'll just go 32 after that. I think I'll run out of room. And we have a similar situation. A little further out left, but the right point is a lot further right. Okay, so maybe we're getting something like this, it looks to me. Actually, maybe right over there somewhere. Okay. And so it's kind of like paraboloid, but like kind of skewed off to one side. Okay. That's the kind of surface we're getting based on these contour plots. Just like with quadric surfaces, we can use traces to help us plot a three-dimensional surface generally, right? Including these two variable functions. Okay, so our function here is z of xy equals root 9 minus x squared minus y squared. So let's start by plotting some, vertical traces. That's when we set x equal to a constant or y equal to a constant. And I always think setting x equal to 0 and y equals 0 is a good start. Okay, so if I set x equal to 0, that's z equals square root of 9 minus y squared. Notice I left off the of xy just for simplicity. It's much easier to think about this as just z than with all of this notation here. Okay? What graph is this? This might not be one that you're super familiar with, but it comes up quite frequently. So if you're not familiar with it, it's a good one to know. Okay? So first, just some intuition on this. Underneath the square root, the inside of the square root has to be non-negative, right? Because I'm subtracting something squared, if y gets big enough, either big enough positive or big enough negative, it will make the inside of the root negative. We don't want that. Okay? So what's the biggest y could be? Well, the smallest the inside of the root would be 0. And the y that would make that happen would be y equals 3. If y gets any bigger than 3, then it would be too big and make the inside of the root negative. Okay? So we know that the biggest we could possibly be is right here at 3. Y equals 3. Here's the y-axis. Here's the z-axis. Okay? And if I plug in y equals 3, it's easy to see that I'll get z equals 0. Right? And the same thing is true for negative 3. Since it's squared, it's going to be a mirror image. Okay? Since the y is squared, we're going to get a mirror image. The z-axis is going to act like a mirror. Because if I plug in a positive y, if I plug in the same y but negative, because it's squared, I'm going to get the exact same thing. Okay? So I cannot go bigger than positive 3 or having a y smaller than negative 3. I have to stay in this region. Also note that z will always be positive because I'm taking a square root, right? This symbol means the positive root. It spits out a positive number. So I know I'm going to be up here somewhere, okay? In between these two values. Somewhere up here. Okay. So I could just plug in some points if I wanted to. I know, for example, if I plug in y equals 0, then I get 3. Okay? And actually, if you plug in enough points, the other points are a little gnarly, but you end up getting a half circle. In this case, the upper half of a circle. Okay, and actually, if you square both sides to get rid of the square root, you can kind of see where this is coming from. if I square both sides, I get z squared equals, and on the right side, the square root goes away. So I get z squared equals 9 minus y squared. If I add the y squared to the other side, I get y squared plus z squared equals 9. And that's the equation of a circle of radius 3. Okay, that's twice what we got. We got half of that, right? Why didn't we get the full circle? Okay, it's because going from this step to this step, when we square things, we lose sign information. When you square something, everything turns positive. Negative turns positive. Positive stays positive. Okay? Now, in this case, we only cared about the positive root. But notice if we stuck a negative in front of that, because we're squaring everything, we get the same thing. Okay? Going from this step to this step, squaring stuff, we lose information. We lose the sign information. And so if we just go with this, we say, oh, we got a full circle. Really, we just have the top half of the circle because we're only letting z equal to a positive number, okay? If we wanted the bottom half, by the way, it'd be the exact same thing, just with that negative in front of the root. Then z could only equal to a negative number, and we'd get the bottom half of a circle, all right? So we have half a circle, okay, in the YZ plane. That's one of our vertical traces. Let me plot this in 3 dimensions. X-axis, Y-axis, Z-axis. Here is our YZ plane. And I'm going to draw a half circle. Let's do 1, 2, 3 out that way. 1, 2, 3 out that way. And then 3 up. Okay. So I'm getting a half circle this way. Okay, so let's do y equals 0 now. The other vertical trace. Okay, I do y equals 0. That would give me z equals square root of 9 minus x squared. Right? Well, that's easy to work with. It's exactly what we got up here. We're just swapping out the x for the y, or the other way around. We're swapping out the y for the x. So in the xz plane, we'll get the exact same thing. We'll get a half circle of radius 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. We're going to go through those 3 points, and we get our half circle. Okay, so that'll be the xz plane. That's the xz plane. We'll go 3 units this way and 3 units this way. And this. Okay, something like that. Okay. All right, we've got our vertical traces. Now let's do our level curves. Remember, the level curves are the traces when you set the function value or the z value equal to constants. Okay. Usually the level curves are the ones that are the easiest to find. So I'm going to find multiple level curves, all right, and make a contour plot with them. So let's start with z equals 0. Notice it's a good idea to know what values you're allowed to plug in. I'm looking at this. Since this z value is equal to a square root, z always has to be positive, okay? So I don't want to look at a level curve where z is negative. That wouldn't make any sense. It wouldn't tell me anything. I want to only look at the level curves in this particular example where the z is positive. So, or I should say non-negative. The smallest z value that's possible, just looking at that, looks to be 0. So I'm going to start with z equals 0, and then I'll maybe do a few more. Okay? So if I do z equals 0, That's 0 equals square root of 9 minus x squared minus y squared. Okay. To plot this, I'm going to go ahead and square both sides. I get 0 equals 9 minus x squared minus y squared. Add x squared and y squared to the other side. Notice a lot of times with these level curves or vertical traces or any kind of trace really, it sometimes takes a little bit of work to put it into a form that we recognize and are able to graph. Okay? So in this case, I had to square, I had to move the x squared and the y squared over. Now I have x squared plus y squared equals 9. That's a circle of radius 3 centered at the origin. Okay? So I'm going to do a few of these level curves, get a little bit of a contour plot going here. So this would be in the xy plane. So we're looking at it from above. At the height z equals 0, I have a circle of radius 3. Let me make it a little bigger since I have the space. Okay. Circle of radius 3. This is z equals 0. A lot of time it's a good idea to if you're doing lots of them, if you're doing a contour plot, good idea to label what your z value is that corresponds to that particular level curve. And that way you know the direction. Are we increasing or are we decreasing as we go out from the origin or as we come in? Okay, you know if you're going up or if you're going down. Do you have a hill? Do you have a valley? Okay, so we did z equals 0. Let's do z equals 1. Okay. If I do z equals 1, I get 1 equals square root of 9 minus x squared minus y squared. Now I'll do the exact same thing. Let's square both sides. And I'm going to move the x squared and the y squared to the left side, and I'll subtract the 1 over to the right. So on the left side, I'll get x squared plus y squared. On the right side, 9 minus 1 is 8. So this is a circle of radius equal to the square root of 8. Square root of 8 is between square root of 9, which is 3, and square root of 4, which is 2. So this is a circle of a radius that's somewhere between 2 and 3. It looks quite a bit closer to 3 than it does to 2, right? Because 8 is a lot closer to 9. So this should be another circle, but just a little shrunken, just with a slightly smaller radius. Okay? So I don't need to be exact here, but I know I want my radius to be between 2. There, that would be a circle of radius 2, and then 3 is the circle I have. I'm going to just shrink it a little bit. Okay, maybe a little bit more just to the pronounced effect. But this is z equals 1. All right, let's go ahead and do z equals 2. And you may already know what this surface is going to look like at this point. But if you don't, you can keep on plotting the level curves or the vertical traces, right? So if I plug in z equals 2, I get 2 equals root 9 minus x squared minus y squared, and I'm doing the exact same thing again. Square both sides. X squared and y squared to the left. And I get 9 minus 4, that's 5 on the right. Now, it's a circle of radius 5. Okay, so another circle. Now it's radius 5. And 5... square root, of radius equal to the square root of 5, not radius 5. The radius squared is 5. 5 is still between the 2 and 3. But now it's a lot closer to 2, right? 5 is a lot closer to 4 than it is to 9. So, another circle. But now, maybe something like that. Closer to 2 than to 3. So that's z equals 2. And let's just do one more. And the reason why I say one more is I cannot possibly go past z equals 3. Z equals 3 is the highest possible z I'm going to have. Why? Remember, I need a positive number under this root. Okay? And because the x squared and y squared are squared, the smallest, the best case scenario that I could get here, because this will be subtracting, the biggest z I could have is when x and y aren't taking away anything, when x and y are both 0. So the best case scenario, the biggest z possible, is equal to the square root of 9, or it's 3. Okay, so z equals 3 is the biggest I could have. I get 3 equals root 9 minus x squared minus y squared. Square both sides. I get 9 equals 9 minus x squared minus y squared. Now we're going to have something a little different go on. Now I get 9 minus 9, that's 0. I can move the x squared and y squared to the other side still. Okay? But now I get x squared plus y squared equals 0. I can't have a circle of radius 0. What's going on here? Well, notice x squared is always non-negative. Y squared is always non-negative. The only way I could add two non-negative numbers and have them both be 0 is if both of those numbers are 0. The only solution here is when x and y are both 0. So there's only one point that makes this last level curve true. And that's this one right here. And that's z equals 3. Okay? So you can kind of see what's going on. At the lowest level, z equals 0, I have a big circle. And as I go up, my circles shrink. But they don't shrink evenly, do they? I start off shrinking pretty quickly. Okay? From this step to this step. I'm sorry, shrinking slowly. I'm going uphill quickly. Right? I'm very steep uphill, but the circle doesn't shrink much. By the time I get to 2, it's shrinking a little faster. And then by the time I get to height 3, it's shrunk all the way. Okay? So if I just kind of plot these, there's the level curve at z equals 0, z equals 1, a little bit more, z equals 2, circle shrunk a little bit more, and then here at the top is that. Okay, I'm getting the upper half of a sphere. Okay, but only the top half. And actually, if we go back to our original function, we can see that if we're experienced enough. Okay, because we get z equals root 9 minus x squared minus y squared. The z has to be positive because of the root. But if I square both sides, I get something similar. Let me straighten this out. It's bugging me. Z equals root 9 minus x squared minus y squared. If we square both sides, it's very similar to what we got with the half circle. Okay, we get z squared equals 9 minus x squared minus y squared. Add the x squared and y squared to the other side. That's the equation of a sphere of radius 3. But because we squared, going from this step to this step, we lost the sign information. So going back to our very first, we're like, okay, we know we are dealing with a sphere, but because of this first step of our original equation, we know z has to be positive. So it's only the upper half sphere, only the part of the sphere where z is positive. Just one more thing I want to talk about before we finish off this section. So far, we've focused on functions of just 2 variables. But there's nothing magical about two variables. We deal a lot with functions of two variables in this class because they are easy to graph. You plug in two variables, you get a third one out. That's a surface of three variables. We can deal with three-dimensional space. Okay, but there's no reason we have to limit our function to just two variables. And in fact, in real life situations, we often deal with many variables in a function. So let me just give you one example. Okay, what if we have a function of three variables? And let's keep it pretty simple. X squared plus y squared minus z squared. Now, first off, I want to note that we cannot visualize this is just a spatial shape because it involves four variables, the three input variables, x, y, z, and then the output variable. That's four variables. We cannot visualize four-dimensional space, all right? What we can do, though, is look at sections of it, much like how we do this with a two-variable function. Instead of looking at the whole two-variable function in one go, we look at level curves or vertical traces of the function. And that takes the three-dimensional full surface and we look at a two-dimensional cross-section. Okay? We can do the same thing for a three-variable function. Rather than dealing with the full four-dimensional aspect of this function, if we set one of our variables equal to a constant, then that reduces it to a three-variable, a three-dimensional cross-section of this four-dimensional hypersurface. Okay? Specifically, if we set the function value equal to a constant, we get a level surface, not a level curve, because we'll still have three variables, right? We're just setting one of the four variables equal to a constant. That will leave us with something with three variables. Okay? So if we, let me put it this way, actually, given a three variable function, and we have x, y, and z, so often we'll treat the output variable. We can't have another variable past z, so we go backwards. We pick w. Okay, so given a three-variable function, w equals f of x, y, z, a level surface of the function is the 3D trace we get from setting the output variable equal to a constant. Okay, so we set the w equal to some constant, maybe 2, maybe 7, maybe -4, right? Bunch of constants to choose from. But then we are left with some equation of three variables. That is a surface in three-dimensional space. We could graph a surface in three-dimensional space. Okay, this would be a cross-section, three-dimensional cross-section of this four-dimensional structure. All right, so let's take this and let's see what that looks like as an example. All right, so I'm just going to pull up our 3D graphing calculator for this. All right, so I have our function x squared plus y squared minus z squared, and then it's set equal to a constant. Right now that constant is set equal to 0. So this is the level surface of our three-variable function. In this case, it's a double cone. All right, now we actually do have a way to kind of visualize how a fourth dimension would work if we allow that fourth dimension to be time. So if we kind of animate this, then we could see how this changes over time by changing that constant. Okay, let me start it on this side, and we'll go slow. So at k equals -5, setting the function value to -5, we get a hyperboloid of 2 sheets. And notice what happens as we let that constant progress. We can imagine this, the constant here being time, the output variable being time, and it gives us a way to visualize and interpret this 4-dimensional hyperstructure. Okay, so as that constant increases, see how it's getting closer and closer together, and then at a moment at k equals 0, let's go back to k equals 0, they just touch. That's the moment we get the double cone, and then after that, it's a hyperboloid of 1 sheet that just gets wider and wider and wider. Okay, so we can use these level surfaces to get some kind of visual intuition on these higher dimensional structures.